In this video, we're going to do a little bit about solutions. Now, most of this stuff we have already gone over this year, but I just want to go over it and make sure it's a nice little review. So here, this question is asking for a resulting concentration of potassium. So the first thing you need to do is figure out how much potassium is in this solution, and then how much potassium is in this solution, and then divide by the combined volume. So I'm just going to go ahead and do millimoles and then milliliters. So if I do 30 milliliters times 0.5 molar, and then I'm going to multiply by the coefficient of 2 because we are looking for potassium here. So don't forget that there are 2 potassiums for every potassium sulfate. That gives me a total of 30 millimoles. And then for KMNO4, I'm going to do 70 times 0.5 molar. And that's just time 1 because we have 1 potassium for every KMNO4. So that gives us 35. We then add these together. We get 65 millimoles. Divide by the total milliliters. So that's 30 milliliters plus 70 because you are pouring these together. So this is a pour together problem. Divide by 100 milliliters because this is millimole. And you get 0.65 molar. So the resulting concentration is 0.65 molar. Again, something we've done before, but nice little review of these basic solutions concepts. This question, asking you with these pictures, which one of these is a non-electrolyte? Non-electrolyte, remember, means it does not conduct electricity. Anything with ions is going to conduct electricity because that's movement of electrons. So our answer here is going to be number 1, because if you look, we have ions in this one, and we have a bunch of ions in this one. So the only one without ions, with no pluses and minuses, is number 1. Let's take a look at this problem. So this is asking you, what is the reaction that best represents the dissolving of magnesium chloride? So the first thing you should do is write the formula for magnesium chloride. Remember, magnesium is 2 plus, chloride is 1 minus. So when we crisscross, MgCl2. So we can automatically get rid of this one and that one because they're not MgCl2. Next question is, when it dissolves in water, what does it become? So magnesium chloride is a chloride salt. So it's going to dissolve into its ions, Mg2 plus and Cl minus. But remember, this is just like when you're writing net ionic equations, because that's basically what we're doing here. This 2 becomes a coefficient. So we should pick the one that has Mg2 plus and 2 Cl minus. So our answer here is going to be number 6. So now we're looking at perchloric acid. Perchloric acid is going to lose its H plus. Okay, but remember that ClO4 is not going to split up because it is a polyatomic. So our answer here is going to be number 1. They all lose their H plus. Okay, this one doesn't work because this 4 means it's not balanced. That 4, because it moved here, it's not like where we moved the 2Cl. Okay, because it is a polyatomic, you can't move that 4 in the polyatomic. Polyatomic has to stay exactly together, so you're not going to move that up here. You're also not going to do that because then it means 4Cl. And we don't have 4Cl on this side, so it's not even balanced. And then this one is balanced, but the problem here is that you're not going to split up a polyatomic. So splitting it up into Cl and O is not going to work. So you want to pick the one that keeps the polyatomic completely together, including the subscript. Here's a quick question about precipitates. Sodium hydroxide combined with aluminum nitrate. So if you want, you can write the net ionic equation. Sodium hydroxide and aluminum nitrate. So that would give you Na plus OH minus plus Al3 plus 3NO3 minus. And when you do your double replacement, you'll end up with NaNO3 plus AlOH3. And I'm just going to balance that. And so on the other side, you would look here. And if you look at these two products, the one that is going to be insoluble is definitely going to be AlOH3, because we know that nitrates and sodium are always soluble. So if you didn't even want to do the full net ionic equation, you don't have to. You can just look at the potential products. But if you did that, you would split up NaNO3, but then you would keep this together because it is the solid. Again, you don't even have to do this. It's a multiple choice question. You don't have to show work. Your answer is going to be number 5. Hopefully you notice that it's not number 2 or number 3, because those are not appropriate formulas for aluminum hydroxide. This one is missing the 3 plus charge on aluminum. That would be crisscrossed. And this one doesn't take into account that OH, hydroxide, is a polyatomic. So here's a little bit about these types of representations of solutions. Okay, so here's some rules about how they work. Atoms are going to be represented by circles. If they have different colors, they will represent different elements. You also might see on a black and white situation different shapes representing different elements, so it won't actually be colored circles. But if the shapes are touching, if the circles are touching, they are bonded together, and if they are not, then they are not bonded. So if we look at this picture, we have some red, whatever red happens to be, solo red atoms, and then we also have 2 red atoms combined into a molecule. And then over here we have a different type of molecule with 1 red and 2 blue, and then we also have some lone blue ones. So let's get a little bit of practice with those types of questions. So here the question is, what is a pure substance? So we're going to look for boxes that have all the same thing. Pure substances can be atoms or they can be molecules, but they're going to all have the same thing. So here in box 1, it's not a pure substance because we have lone blue and lone red. Here in box 2, it's also not a pure substance. Although these are all blue, some of them are blue 3, so something like this, and some of them are blue 2, and BL I'm just using for blue. Those are not the same exact thing. You might be confused by that, but that is not a pure substance. That's actually an allotrope of one element. Okay, so for example, oxygen does that. There's O2, which is just oxygen gas, and O3, which is ozone. Those are allotropes of oxygen. Number 3 is not a pure substance because we have red 2 and blue 2. Number 4 doesn't work. We have lone red, lone blue, and then this funny molecule. Number 5, all we have is lone red. So that one is a pure substance. And number 6, we have only molecules that are blue and red attached. There's nothing else mixed in there. So that's a pure substance, even though it is a compound. 7 is not, because we have some that are double red and some that are blue-red, so it's not all the same. So this one, which boxes contain mixtures whose particles are atoms and molecules? Number one, not, because they're all atoms. Number two, they're all molecules. Number three, they're all molecules. Number four, we have some atoms and some molecules. 5 and 6 are not mixtures. Pure substances are not mixtures. Mixtures are different from pure substances. A mixture is two or more pure substances that are physically combined. And then 7 is a mixture, and it is all molecules. Oh, it's all molecules, so that doesn't work to fit our description of atoms and molecules. So only number 4 fits that description. So here's a little bit of a summary of different types of stuff that you can have. So we have pure substances, mixtures, just some definitions here. Element, compound, atoms, molecules. Now you'll mostly hear molecules for covalent compounds. You might hear formula units or even ionocules for ionic compounds, but molecules will be covalent compounds. But here's just a summary of those definitions, which I think you're all aware of, but just to throw this in your notes and use as a review. So here's a flow chart for people who might want to see it kind of done out in a visual way. Pure substances can be split up into elements and compounds. Mixtures can be split up into heterogeneous, so you can see the different parts. You can see like different parts of the mixture, like trail mix or something. Homogeneous mixtures, which are solutions. You can't see the different parts. Regardless of what type of mixture you have, these 3 yellow boxes on the bottom are appropriate. 2 or more different substances, physically mixed, not chemically bonded, and they can have a variable ratio, meaning that you can have more nuts than raisins in your trail mix, and the next time you make it, you can have more raisins than nuts. It doesn't matter, it's still a mixture. Compounds are chemically combined, so they are in a fixed ratio. That we know that like H2O, water is always H2O no matter how much of it you have. If it's not H2O, it's no longer water. So here are the 2 major types of mixtures. So you also have that in your notes. And then underneath at the bottom, we have different types of solutions that you can have. Okay, so you can have a bunch of different types, but when you look at it, it is going to be uniform and you're not going to see any differences.